Good day. I will be discussing capacitance and dielectrics. Now let's start with capacitors. Any two conductors separated by an insulator or a vacuum form a capacitor. A capacitor is a device that stores electric potential energy and electric charge. To store energy in a capacitor, transfer charge from one conductor to the other so that the one has a negative charge and the other has an equal amount of positive charge. To move the charges through the resulting potential difference between the conductors, work must be done, and this work done is stored as electric potential energy. Now, when we say that a capacitor has charge Q, or that charge Q is stored on that capacitor, it means that the conductor at higher potential has charge positive Q and the conductor at lower potential has charge negative Q, assuming that Q is positive. In circuit diagrams, a capacitor is represented by either these two symbols. The vertical lines in either symbols, the straight or the curve, represent the conductors, and the horizontal lines, these horizontal lines, represent wires connected to either conductor. Now, how to charge a capacitor? One common way to charge a capacitor is to connect these two wires to opposite terminals of a battery. Once the capacitor is connected to the voltage source or the battery, it will charge up to its output voltage. The electric field at any point in the region between the conductors is proportional to the magnitude Q of charge on each conductor. It follows that the potential difference V sub AB between the conductors is also proportional to Q. For a particular capacitor, the ratio of the charge on each conductor to the potential difference between the conductor is constant, called the capacitance. Capacitance is given with an equation C is equal to Q over V. This is now our first equation, where Q is the charge and V is the potential difference. The SI unit of capacitance is farad with symbol capital letter F, in honor of the 19th century English physicist Michael Faraday. And from the equation, 1 farad is equal to 1 coulomb per volt. From the equation 1, C is equal to Q over V, the greater the capacitance of a capacitor, the greater is the magnitude of charge in either conductor for a given potential difference V, and hence the amount of stored energy. Thus, capacitance is a measure of the ability of a capacitor to store energy. Let's have capacitor in a vacuum. We can calculate the capacitance C of a given capacitor by finding the potential difference V between the conductors for a given magnitude of charge Q. So in here, we will consider capacitors in vacuum, that is, we'll assume that the conductors that make up the capacitor are separated only by empty space. And the simplest form of capacitor consists of two parallel conducting plates, each with area A separated by a distance d that is small in comparison with their dimensions. So when the plates are charged, the electric field is almost completely localized in the region between the plates. The field between such plates is essentially uniform, and the charges in the plates are uniformly distributed over their opposing surfaces. Now this is our drawing. This is the wire. The plate A with area A has charge positive Q, and plate B with area A has charge negative Q, and this is their separation distance. and this is our potential difference V sub AB. Now, using Gauss' law, we found that the electric field of an infinite plane is equal to E is equal to sigma over epsilon naught, where sigma is the magnitude of the surface charge density on each plate. This is equal to the magnitude of the total charge Q on each plate divided by the area A of the plate, or sigma is equal to Q over A. Substituting here, we have our sigma Q over A over our epsilon naught, so the field magnitude can be expressed as like this. The field is uniform and the distance between the plates is d, so the potential difference between the two plates is equal to VAB equals ED, where E is the electric field and D is the distance. And it is equal to our electric field, which is Q over epsilon naught A, and our D, and we can rewrite this as 1 over epsilon naught Q D over A. So from equation 1, which is C is equal to Q over V, our Q, so we can express this as Q over our V sub AB, which is equal to 1 over epsilon naught QD over A. Cancel our Q here, so we have epsilon naught A over D. This is now our equation 2, the capacitance of a parallel plate capacitor in vacuum. Now let's have an example. That the plates of a parallel plate capacitor in vacuum are 5.5 millimeter apart and 2 meters squared in area. A 10.0 kilovolt potential difference is applied across the capacitor. Letter A, compute the capacitance. Letter B, the charge on each plate. And C, the magnitude of the electric field between plates. So for our letter A, we have to compute the capacitance. And to find the capacitance C, we use the equation 1, equation 2 rather. C is equal to epsilon naught A over D, which is our epsilon naught is given with 8.85 times 10 to the negative 12 farad per meter times our area, which is 2 meters squared, over separation distance 5.5 times 10 to the negative 3 meter, since it is given as a millimeter. And our capacitance now is equal to 3.22 times 10 to the negative 9 farad, or equal to 0.0032 microfarad. Cancel our M here and the other M, so we only left with the unit farad. So from equation 1, C is equal to Q over V, we can find the charge of the capacitor. Q is equal to CV. Substitute our capacitance is 3.22 times 10 to the negative 9 farad times the potential difference, the 10 times 10 to the 3 volts. So we have 3.22 times 10 to the negative 5 coulomb, or equal to 32.2 microcoulomb. The plate at higher potential has charge positive Q, so our charge is equal to positive 32.2 microcoulomb, and the other plate has a negative charge, so it has negative 32.32 microcoulomb. Now, for our letter C, we are to find the electric field magnitude. So we can use the formula E is equal to sigma over epsilon naught, which is equal to Q over epsilon naught A. Our Q, 3.22 times 10 to the negative 5 coulomb over the value of our epsilon naught, which is equal to 8.85 times 10 to the negative 12 c squared per n dot m squared times our area, which is 2 meter squared. So cancel m squared here, cancel our c, and we have 1.82 times 10 to the 6 Newton per coulomb. This is now our electric field. We can also find electric field by recalling that the electric field is equal in magnitude to the potential gradient. So the field between the plates is uniform, and from V sub AB is equal to ED, we can find E is equal to V sub AB over D. We have potential difference 10 times 10 to the 3 volts over our separation distance 5.5 times 10 to the negative 3 meter, and we have 1.82 times 10 to the 6 volts per meter. And remember that 1.1 Newton per coulomb is equal to 1 volt per meter. So either we use this equation or we use the E is equal to Q over epsilon naught A, we still arrive the same answer. Capacitors in series. We have here a drawing of a series connection network. This is our VAB, which is equal to our potential difference V. We have point E, point A, point C, and point B. This is positive Q, positive Q, negative Q. This is our C1, our C2, and from the top to our point C, that is our potential difference from A to C, which is our V1, and from point C up to the bottom, that is our potential difference from C to B, that is equal to V2. So in series connection, the magnitude of charge on all plates is the same, and that is QT is equal to Q1 is equal to Q2. We can write the potential differences. In here, we can write the potential differences from point A and C, C to B, and A to B as potential difference from point A to C equals V1 equals Q over C1. Potential difference from point C to B is equal to V2 is equal to Q over C2. Now for our potential difference from point A to B, we can see here that from point A to B, that is we can say that that is our total V. So that is equal to V, which is equal to V1 from point A to C plus V2 from point C to B. This is equal to Q times 1 over C1 plus 1 over C2. We factor out Q here since our charge on series connection is the same across the combination. And so V over Q is equal to 1 over C1 plus 1 over C2. This is now our equation 3. We use the symbols V1, V2, and V to denote the potential differences. Potential difference from point A to C across the first capacitor, potential difference C to B across the second capacitor, and V, AB across the entire combination of capacitors respectively. So our equivalent capacitor then would look like this. This is our potential difference B, our point A, point B, positive Q, negative Q, and our C equivalent, which is equal to Q over V from our equation 1 from the capacitance C is equal to Q over V. Now, the equivalent capacitance C equivalent of the series combination is defined as the capacitance of a single capacitor for which the charge Q is the same as for the combination when the potential difference V is the same. In other words, the combination can be replaced by an equivalent capacitor of capacitance C equivalent. C equivalent is equal to Q over V, or 1 over C equivalent is equal to V over Q. This would be our equation 4. Now, combining equation 3, which our equation 3 is V over Q is equal to 1 over C1 plus 1 over C2. Combining this equation 3 with equation 4, we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2. If we have many number of capacitors, then the equivalent capacitance would be 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus ... 1 over Cn. This is now our capacitance in series, and this would be our equation 5. Now, this capacitance in series, the reciprocal of the equivalent capacitance of a series combination equals the sum of the reciprocals of the individual capacitances. Remember also that in series, the equivalent capacitance is less than the individual capacitances. Capacitors in parallel. We have here an illustration of a parallel connection. This is our VAV which is equal to V, our potential difference. We have point A, point B. This is our C1, Q1, C2, Q2. In parallel connection, the potential difference for all individual capacitors is the same and is equal to VAB equals V. The charges on each capacitor depends on its capacitance, which is given as Q1 equals C1V and Q2 equals C2V. The total charge Q of the combination can be written as Q T is equal to Q1 plus Q2 equals C1 plus C2 times V. Our Q1 is C1V, our Q2 is C2V, but since our potential difference in a parallel connection is the same, so we can write it as C1 plus C2 times V. So again, since the potential difference is the same across the combination, so Q over V equals C1 plus C2. And this would be our equivalent capacitor or equivalent capacitor in parallel. This is our potential difference, our point A, point B. This is positive Q, negative Q, and our C equivalent, our Q, which is equal to Q1 plus Q2. The parallel combination is equivalent to a single capacitor with the same total charge Q is equal to Q1 plus Q2 and potential difference V as the combination. The equivalent capacitance of the combination C equivalent is the same as the capacitance Q over V of the single equivalent capacitor. So from equation 6, Q over V. By the way, this is our equation 6. Q over V equals C1 plus C2. So from equation 6, Q over V is equal to C1 plus C2. We can rewrite this as C equivalent is equal to C1 plus C2. Now for any number of capacitors in parallel, C equivalent is equal to C1 plus C2 plus C3 plus Cn. And this is now our capacitance in parallel, which would be our equation 7. The equivalent capacitance of a parallel combination equals the sum of the individual capacitances. Let's have an example. The illustration. This is a 3 microfarad capacitor, 11 microfarad capacitor, 12 microfarad capacitor, 6 microfarad capacitor, and 9 microfarad capacitor from point A to point B. This combination is both a series and a parallel combination. So, the question here, we are to find the equivalent capacitance of the 5 network capacitor. And as we see, our network is a combination of series and parallel connection. So first, we can see that the 12 microfarad capacitor and the 6 microfarad capacitor are in series. So to find its equivalent capacitance, we use equation 5. That is 1 over C equivalent is equal to 1 over C1 plus 1 over C2, or this is equal to C equivalent equals 1 over C1 plus 1 over C2 inverse. So C equivalent are C1 1 over 12 microfarad plus 1 over 6 microfarad inverse, and our C equivalent is 4 microfarad. Since we combine the 12 microfarad and 6 microfarad capacitor and its equivalent is capacitance is 4 microfarad, our reduced network would look like this. This is from point A to B. This is our 11 microfarad capacitor, our 9 microfarad capacitor, and this would be our 4 microfarad capacitor and our 3 microfarad capacitor. So this would now be our reduced network. Now, as we can see here, the 3 microfarad capacitor, the 11 microfarad capacitor, and the 4 microfarad capacitor are connected in parallel. So to find the equivalent capacitance, we use equation 7. That is, C equivalent is equal to C1 plus C2 plus C3. Our C1 equals 3 microfarad plus 11 microfarad plus 4 microfarad, and our C equivalent is equal to 18 microfarad. Then our current network would be, our reduced current network would look like this. This is our 18 microfarad capacitor. This is our 9 microfarad capacitor that is from point A to point B. Now, we are left with only these two capacitors. And since they are connected in series, so we have to use equation 5 again. C equivalent is equal to 1 over C1 plus 1 over C2 inverse. And we have 1 over 18 microfarad plus 1 over 9 microfarad inverse. And our C equivalent would be 6 microfarad. And this is how it looks like. It looks like our 6 microfarad capacitor. If we are given the potential difference across the entire network as V sub AB as 9 volts, then the net charge in the network is equal to Q equals C equivalent V sub AB, which is equal to our C equivalent, which is 6 microfarad times RV 9 volts. This is equal to 54 microcoulomb. This is now our net charge. We now have a potential difference of 9 volts and a net charge of 54 microcoulomb. Now we have to find the voltage across and the individual charge on each of the 5 capacitors. So For 12 microfarad and 6 microfarad capacitor in series, their C equivalent is equal to 4 microfarad. And we have our voltage VAV equals 9.0 volts. So to find the net charge, Q equals C equivalent VAB, or C equivalent is equal to 4 microfarad times our V, which is 9 volts. So we have 36 microcoulomb net charge. Now to find the individual voltage across, we have for our V1, we have V1 equals Q over C1. Our net charge is equal to 36 microcoulomb over our first capacitor, 12 microfarad, and we have 3 volts. For our second voltage, we have V2 equals Q over C2. Our net charge is equal to 36 microcoulomb and our second capacitor is 6 microfarad. So this is equal to 6 volts. Now, since this is in series connection, the total voltage is equal to the sum of the individual voltage, and if we add the two voltage, 3 volts plus 6 volts, this is equal to 9 volts, which is the net potential energy or net voltage across the network. Now let's move on to the for 3 microfarad capacitor, 11 microfarad capacitor, and 4 microfarad capacitor in parallel. Their equivalent capacitance is 18 microfarad as we have solved earlier. And we have our V sub AV, which is 9 volts. This is the same, our voltage here is the same across, which is 9 volts, since this is in parallel connection. So we have to find the individual charges. For our Q1, we have Q1 equals C1V. Our first capacitor is 3 microfarad times our V, 9 volts. This is equal to 27 microcoulomb. For our second capacitor, Q2 equals C2V. Our second capacitor is 11 microfarad times 9 volts, and we have 99 microcoulomb for our second charge. For the value of our third charge, we have Q3 equals C3V. Our third capacitor is 4 microfarad times 9 volts, and this is equal to 36 microcoulomb. Since this is in parallel, the net charge is equal to the sum of the individual charges. So Q net equals Q1 plus Q2 plus Q3. Our Q1 is equal to 27 microcoulomb plus 99 microcoulomb plus our third charge. The value of our third charge is 36 microcoulomb. Adding these three charges, we have our net charge 162 microcoulomb. Now for our 18 microfarad and 9 microfarad capacitor in series, their equivalent capacitance is 6 microfarad. And we have our voltage 9.0 volts. So to find the net charge, we have C equivalent times VAB. Our C equivalent is 6 microfarad times our voltage 9 volts, and this yields 54 microcoulomb for our net charge. And finding the individual voltage, V1 equals Q over C1, 54 microcoulomb over our first capacitor, 18 microfarad. This is equal to 3 volts. For our V2, Q over C2, 54 microcoulomb over our second capacitor, 9 microfarad. So 54 divided by 9, we have 6 volts. And again, this is in series connection, and the total voltage across is equal to the sum of the individual voltage. So we have 3 volts plus 6 volts equals 9 volts. This is our net voltage, 9 volts. Now let's go to energy storage in capacitors. For capacitor stored energy, the electric potential energy stored in a charged capacitor is just equal to the amount of work required to charge it. So when the capacitor is discharged, this stored energy is recovered as work done by electrical forces. And we can calculate the potential energy U of a charged capacitor by calculating the work required to charge it. Suppose that when we are done charging the capacitor, the final charge is Q and the final potential difference is V. So from equation 1, C equals Q over V, we can relate these quantities as V equals Q over C. Let Q and V be the charge and potential difference respectively at an intermediate stage during the charging process. Then V equals Q over C. At this stage, the work dW required to transfer an additional element of charge dQ is equal to dW equals V dQ. And since our V is equal to Q over C, we can write this as Q dQ over C. So the total work required or needed to increase the capacitor charge Q from 0 to final value is just W equals integral of dW, that is from 0 to W, and this is equal to our dWq 1 over C. We can write 1 over C out on the outside of the integrand, since it is constant as a function of Q, constant with respect to Q. So 1 over C integral of Q dQ, that is from 0 to Q. So integral of Q dQ, this is equal to Q squared over 2, and we can write C here since our C is constant. So this is the work to charge a capacitor, and we can denote this as our equation 8. The unit of our potential energy is in joules since it is energy. To find the energy stored in a capacitor, the formula of a potential energy stored in a capacitor, we have the expression of a current I equals dQ over dt. And since Q is just equal to CV, as we can recall, we can write this as d times CV over dt. And we can write this further as C times dV over dt. By rearranging this equation, we can calculate the voltage across the capacitor as a function of the displacement current. So from I equals C over dV, we have dV equals 1 over C I dt. In getting the V, we use integration. This is integral of dv equals integral of 1 over c I dt. So this is now equal to v equals integral of 1 over c I dt. But since our 1 over c here is constant with respect to time, we can write this as v equals 1 over c integral of I dt. Unlike a resistor, a capacitor does not dissipate energy. Instead, a capacitor stores energy in the form of electric fields between its plates, which can be recovered later when it discharges. So to find the energy W stored in a capacitor, we take both the expression of electrical power, P equals IV, and the expression for the definition of power, P equals dW over dt, and we combine them. So do the math to get the work. IV equals dW over dt. So IV dt equals dW. To get the energy W, we have to integrate this. Integral of IV dt equals integral of dW. So this is equal to integral of IV dt equals W. And W equals integral of, since our I can be written as C equals dV over dt and V dt. So we can cancel this dt and we are left with work equals C dV, CV integral of CV dt dV, and simplify, we have work equals CV squared over 2. This is one of the formula in the potential energy stored in capacitor. But since our C here can be equated as Q over V, so we have W equals, our C, it can be equated as Q over W, Q over V I mean, times V squared over 2. Cancel the V, we have W equals Q V over 2, or 1/2 QV. This is the other formula in getting the potential energy stored in a capacitor. If we define the potential energy of an uncharged capacitor to be 0, then the W in equation 8 is equal to the potential energy U of a charged capacitor. So the final stored charge is Q equals CV. So we can express U, which is equal to W, as U equals Q squared over 2C. This is from our equation 8, and equals 1/2 CV squared equals 1/2 QV. This is now the formulas in getting the potential energy stored in a capacitor, and we can denote this as our equation 9. Electric field energy. By moving electrons directly from one plate to another, we can charge a capacitor. This requires doing work against the electric field between the plates. So we can think of the energy as being stored in the field in the region between the plates. To develop this relationship, let's find first the energy per unit volume in the space between the plates of a parallel plate capacitor with a plate area A and separation distance D. We call this the energy density, denoted by small letter u. From equation 9, the total stored potential energy is just equal to 1/2 CV squared, and the volume between the plates is just AD. Hence, the energy density is just equal to the stored potential energy 1/2 CV squared over the volume between the plates, AD. Now this is our energy density, which denoted by a small letter u, and we can denote this as our equation 10. As we can recall from equation 2, the capacitance C is given by C equals epsilon naught over AD. That's for the parallel plate capacitor. The potential difference V is related to the electric field magnitude E by V equals ED. So if we use these expressions in our equation, U equals 1/2 RC is equal to epsilon naught A over D times our V, which is equal to ED squared all over AD. If we use these expressions, the geometrical factors A and D, this A cancel with A, D cancel with the other D here, and we find U equals 1/2 epsilon naught E squared. This is now the electric energy density in a vacuum, the formula of our electric energy density in a vacuum, and we can denote this as our equation 11. This relationship is valid for any capacitor in vacuum, and indeed for any electric field configuration in vacuum, although this was derived only for a parallel plate capacitor. The implication of this equation 11 is somewhat interesting. We used to think of a vacuum as space with no matter in it, but vacuum can nevertheless have electric fields and therefore energy. Thus, empty space need not to be truly empty after all. Let's have an example. Problem A. What is the magnitude of the electric field required to store 1 joule of electric potential energy in a volume of 1 cubic meter in vacuum? So first, we are to find the electric field, and we are given with the electric potential energy or energy density of U equals 1 joule per cubic meter. To find the electric field, we use equation 11. U equals 1/2 epsilon naught E squared. But since we want to find the electric field E, then we can derive the formula. So our formula would be 2U over epsilon naught equals E squared. Extracting this square root, we have square root of 2U over epsilon naught equals square root of E squared. This is equal to E equals square root of 2U over epsilon naught. Substituting the value, we have square root of 2 times RU, which is 1 joule per cubic meter, over the value of the epsilon naught, 8.85 times 10 to the negative 12 C squared per n dot m squared. And this is equal to 4.75 times 10 to the 5th Newton per coulomb. This is now our electric field. This is also equal to 4.75 times 10 to the 5th volt per meter, since 1 Newton per coulomb is just equal to 1 volt per meter. If the field magnitude is 10 times larger than that, how much energy is stored per cubic meter? From our equation 11, we can see that U is proportional to E squared. So if E increases by a factor of 10, then U increases by a factor of 10 squared equals 100. 10 squared, that would be 10 squared equals 100. So for question B, if U increases by a factor of 10, so our energy density U becomes 100 joule per cubic meter if it increases as a factor of 10. Now let's go to dielectrics. Dielectrics are non-conducting material placed between the conducting plates that separate the conductors to the capacitor. So the original capacitance C0 is given by C0 equals Q over V0, and the capacitance to the dielectric present is given as C equals Q over V. This is the original capacitance C0, and this is the capacitance with the dielectric present. So the charge Q is the same in both cases, and V is less than V0. So we conclude that the capacitance C with the dielectric present is greater than C0, because V is much less than V0. So the lesser the V, the greater the capacitance. When the space between plates is completely filled by the dielectric, the ratio of C to C0 equal to the ratio of V0 to V is called the dielectric constant of the material. Dielectric constant, that is K equals C over C0. This is now the definition of dielectric constant, and we can denote this as our equation 12. When the charge is constant, Q equals C0 V0 equals CV, and C over C0 equals V0 over V. So in this case, equation 12 can be written as V equals V0 over K. This is when charge Q is constant. This is now our equation 13. With the presence of dielectric, the potential difference for a given charge Q is reduced by a factor K. The value of K for different materials are given in the book. It's given in a table, dielectric constant for different materials. Induced charge and polarization. When a dielectric material is inserted between the plates while the charge is kept constant, the potential difference between the plates decreases by a factor of K. Therefore, the electric field between the plates must decrease by the same factor. If we denote C0 as the original capacitance and C as the capacitance with a dielectric, then we can also denote E0 as the vacuum value and E is the value with the dielectric. Then E, electric field, is equal to E0 over K. This is when charge Q is constant. And we denote this as our equation 14. Since the electric field magnitude is smaller when there is a dielectric present, the surface charge density must be smaller as well. So we have here an illustration. Figure A is the electric field lines with vacuum between the plates. This is just vacuum between the plates. And for the illustration B is the electric field lines with dielectric between plates. This is the dielectrics. The surface charge on the conducting plates does not change, but an induced charge of the opposite signs appear on each surface of the dielectric. The dielectric was neutral, and the induced surface charges arise as a result of polarization. Now, polarization is a redistribution of positive charge and negative charge within the dielectric material. So for a given charge density sigma, the induced charges on the dielectric surfaces reduces the electric field between lines. So for a given charge density sigma, this induced charge on the dielectric surfaces, this reduces the electric field between plates. We can derive a relationship between this induced surface charge and the charge on the plates. So let's denote the induced surface charge density by sigma I. This is our induced charge, and the magnitude of the surface charge density on the capacitor plates is sigma. Then the net surface charge on each side of the capacitor has magnitude sigma minus sigma I. This is the net surface charge on each side of the capacitor. So the field between the plates is related to the net surface charge density by E equals net sigma over epsilon net. This is the field between the plates. This is related to the net surface charge density E equals Q sigma net over epsilon naught. So for without dielectric, we denote that as epsilon naught. Electric field without dielectric is equal to sigma over epsilon naught. But for electric field with dielectric, we denote that as E, and that is equal to sigma minus sigma I over epsilon naught. We can denote this both as our equation 15. Using this expression in equation 14 and rearranging the result, equation 14 we have E equals E naught over K. So rearranging that with equation 15, we find sigma I equals sigma times 1 minus 1 over K. Now this is the induced surface charge density, and we can denote this as our equation 16. This is the formula in getting the induced surface charge density. This equation shows that when K is very large, then sigma I is nearly as large as sigma. In this case, sigma I nearly cancels with sigma, and the field potential difference are much smaller than their values in vacuum. The product K epsilon naught is called the permittivity of K epsilon naught. This is called the permittivity of the dielectric, denoted by epsilon. So we can write epsilon equals K epsilon naught. This is the permittivity of a dielectric, and we can denote this as our equation 17. In terms of epsilon, we can express the electric fields within the dielectric from equation 14, which is E equals E naught over K. We can express this since our epsilon naught is equal to sigma over our E naught is equal to sigma over epsilon naught, and K from the formula of the permittivity, K is equal to epsilon over epsilon naught. So cancel the epsilon naught, and we are left with sigma over epsilon. So E equals sigma over epsilon. We can denote this as our equation 18. This is electric field in terms of epsilon. So the capacitance when the dielectric is present is given by C equals K C naught equals K or C naught epsilon naught A times D, and since K epsilon naught is just equal to epsilon or the permittivity, we can write this as epsilon A over D. This is the capacitance when the dielectric is present. For the parallel plate capacitor, and we can denote this as our equation 19. And for the electric energy density in a dielectric, as you can recall, equation 11 for energy density in a vacuum, U is equal to 1/2 epsilon naught E squared. This is our energy density in a vacuum. And for energy density in a dielectric, this becomes U equals 1/2 K epsilon naught E squared. And again, this K epsilon naught is just equal to our epsilon, so we can write this as 1/2 epsilon E squared. This is now our equation 20. The energy density and a dielectric, and this one here, this is our energy density in a vacuum, which is our equation 11. So in equation, if K equals 1, epsilon is equal to epsilon naught, and equations 19 and 20 reduce to equations 2 and 11, which is the formula for the capacitance and energy density in a vacuum respectively for a parallel plate capacitor. For this reason, epsilon naught is sometimes called the permittivity of free space or the permittivity of a vacuum. Now let's go to dielectric breakdown. Dielectric breakdown takes place when a dielectric material is subjected to a sufficiently large electric field. And when dielectric breakdown happens, the dielectric becomes a conductor. Now how did this happen? This happens when the electric field is so strong that electrons are ripped loose from their molecules and crushed into other molecules, liberating even more electrons. This avalanche of moving charge forms a spark or arc discharge. Now the lightning is a dramatic example of dielectric breakdown in air. It forms a spark or arc discharge. Now this is also the reason why capacitors always have maximum voltage ratings. When a capacitor is subjected to excessive voltage, an arc may form through a layer of dielectric, burning or melting a hole in it. This arc creates a short circuit between the conductors. When this happens, the capacitor rendered permanently useless. So when the arc creates a short circuit, then the capacitor will be useless. Dielectric strength. Dielectric strength is the maximum electric field magnitude that a material can withstand without the occurrence of breakdown. This quantity is affected significantly by temperature, trace impurities, small irregularities in the metal electrodes, and other factors that are difficult to control. For this reason, only approximate figures for dielectric strength is given. The list of the dielectric strengths of a few common insulating materials is given in the UP book. You can see it there. It's in the table, the list of dielectric strength for a few common insulating materials. Let's go to the molecular model of induced charges. We have molecular model of induced charges. How can surface charge arise? Or how can surface charges arise? If a material were a conductor, the answer would be simple, because conductors contain charge that is free to move, and when an electric field is present, some of the charge redistributes itself on the surface so that there is no electric field inside the conductor. But an ideal dielectric has no charges that is free to move, so how can a surface charge occur? To understand this, we have to look at the rearrangement of charge at the molecular model. Some molecules, such as H2O, have equal amounts of positive and negative charges, but a lopsided distribution, with excess positive charge concentrated on one side of the molecule and the negative charge on the other side. This arrangement is called an electric dipole, and the molecule is called a polar molecule. Now, in the figure A is the absence of electric field with no electric field. So, in the absence of electric field, the polar molecules orient randomly. So, as we can see, these polar molecules here are randomly oriented. But when there is an electric field, as in figure B, the molecules tend to align with it. But because of the thermal agitation, the alignment of the molecule with the electric field is not perfect. We also have here non-polar molecules. So figure A is without an electric field, and figure A is with an electric field. So with the presence of electric field, the molecule's positive and negative charges separate slightly, making the molecule effectively polar. It becomes a dipole. However, with the absence of electric field, as in figure A, the nonpolar molecules are not electric dipoles, because the electric field is the one that pushes the positive charges in the molecules in the direction of the field and pushes the negative charges in the opposite direction. This causes a redistribution of charge within the molecule, which is otherwise called as a polarization. Now, these dipoles are called induced dipoles. These dipoles here. So, as we can see here, a figure, polarization of a dielectric in an electric field. This is the electric field. This polarization of a dielectric in an electric field E gives rise to thin layers of bound charges on the surfaces, creating surface charge densities negative sigma I, and sigma I. So with the polarization of a dielectric in the electric field, it gives rise to thin layers of bound charges on the surfaces, thus creating a surface charge density, the sigma I and negative sigma I. The illustration showed the behavior of a slab of a dielectric. This illustration here show the behavior of a slab of dielectric when it is inserted in the field between a pair of oppositely charged capacitor plates. This side is the positively charged capacitor, and this side is the negatively charged capacitor. So this is surface charge density sigma, and here is the surface charge density negative sigma. This is the electric field. So in figure A, this is the original field with no dielectric, only a vacuum between the two oppositely charged plates. Now in figure B, in this figure, this is now after the dielectric has been inserted. This is the dielectric. This one is inserted between the two oppositely charged capacitor plates, the positive charge and the negative charge. And this is before the rearrangement of charges has occurred. So before the rearrangement of charges, this is the illustration looks like. This is the electric field. And figure C, this shows the additional field set up in the dielectric by its induced surface charges. So the additional field is shown by this black arrow here, which has negative and positive on each side. So this is the additional field in dielectric by its induced surface charge density. So this is the original electric field, and weaker field, this is the weaker field in dielectric due to induced charges or the bound charges, which is not the free charge. And this figure D this is now the resultant field. We can see that it has only a few electric field because this few electric field is caused by the induced charges on the dielectric surface, thus reducing the electric field between the plates. This is our induced charge. This induced charge causes to reduce the electric field. Now, polarization is also the reason a charged body such as an electrified plastic rod can exert a force on an uncharged body such as a bit of paper or a piece ball. Now let's go to the Gauss law in dielectric. We have here an illustration. This is the side view. We have a conductor in the right side and a dielectric in the left side. So the electric field on the conductor is 0, and the electric field and the dielectric is E. Now this box here is the Gaussian surface. And if we see that on a perspective view, this is how it looks like. This is the conductor in the right side, the dielectric on the left side, and this is the Gaussian surface. So let's apply Gauss law to the rectangular box shown in this cross section. As we can see, the surface area of the left and right series is A. So as I've discussed, the left side is embedded in the conductor that forms the left capacitor, and the right side rather is embedded with a dielectric where the electric field has magnitude E, and E perpendicular is equal to 0 everywhere on the 4 other sides. So the total charge including both the charge on the capacitor plate and the induced charge on the dielectric surface is enclosed equals sigma minus sigma I times the area A over epsilon. This is just it. This is our Q enclosed, sigma minus sigma I times the area A. So Gauss law gives us EA equals our Q enclosed, which is sigma minus sigma I times area A all over epsilon naught. This is now our equation number 21. This equation relates two unknown quantities: the electric field inside the dielectric and the induced surface charge density sigma I. But we can use equation 16. Sigma I equals sigma times 1 minus 1 over k, or this is sigma minus sigma over k. Or we can write this as sigma minus sigma I equals sigma over k. To simplify this equation, by eliminating sigma I, we combine this with equation 21. EA equals sigma minus sigma I times A all over epsilon naught. So this becomes EA equals sigma A over K epsilon naught. Or we can write this as KEA equals sigma A over epsilon naught. This is our equation 22. This equation says that the flux of KA, not the E alone, through the Gaussian surface of our figure is equal to the enclosed free charge sigma A divided by epsilon naught. It turns out that for any Gaussian surface, whenever the induced charge is proportional to the electric field in the material, we can rewrite Gauss' law as closed surface integral KE dot dA equals Q enclosed free over epsilon naught, where our Q enclosed free is the total free charge enclosed by a Gaussian surface. The significance of this result is that the right sides, as we remember on our illustration, that the significance is that the right sides contain only the free charge in the conductor, not the induced charge.